Decision 2, network problems. The worst sort or the hardest sort of network flow problems tend to be the ones where there's minimum and maximum capacities on each of the arcs, as you can see we've got here. So hopefully it'll help if I go through this exam question. Typically the first part of the question is asking you to find a feasible flow. Well, it's got a feasible flow started here. Says here a feasible flow of 10 litres per second from S to T. Well, you can see here from the source you have 4 and 6, so you have the 10 flowing out, and then into the sink we have 8 through QT, so obviously the other 2 will come from NT. Typically the first part of the question for 4 marks wants you to complete this initial flow by adding the values that haven't been filled in. So we can start with that 2 from NT. We now have 10 going out of the source, 10 coming into the sink. If we look at some of the others, well, Q here. So if we look at Q, we can see we've got 8 flowing out of node Q and only 1 flowing in. The only other arc flowing in is PQ, so we would need to put 7 there. If we now look at N here, we have this going in and we have 3 going out, so we can't deal with that yet. However, we've got 6 here going into M, and the only arc going out is MN, so that must be 6. That's now going to enable us 2 plus 1 is 3, so we must have 3 here. It should all now add up. So we've got 6 going in here, 2 going out there, another 3 going in here, so that's the 3 and 4 for 7. So now it all makes sense, and that's the first 4 marks dealt with. It says here, taking your answer from part A as an initial flow, use flow augmentation on figure 4 to find the maximum flow from S to T. So we compare our minimum and our maximums and our flows to decide what values we put on our forward and backward arrows. So we'll start off by putting forward and backward arrows on every edge. Okay, well, from S to M we have a flow of 4. That could potentially reduce by 1, and it could potentially go up by 5. These 2 numbers here should correspond to the difference between the minimum and the maximum. Here we have a flow of 6, so that could go up by 2, down by 1 to 5. Here we have a flow of 2, so it could go down by 1, up by 2. Q to T, we've got 8 and 12. We have a flow of 8, so could go up by 4. Here we've got 5 and 11 and 7, so could go down by 2, could go up by 4. S to P, 6 and 8, we've got 6, so that's 0, 2. From N to P, we've got a flow of 3, that's the minimum. So it can't go down by any, but it could go up by 3. And then from N to Q, we've got 1, so it could go down by 1. And it could go up by 3. What we now want to do is use flow augmentation to try and find some augmenting routes to add to the flow of 10. So across the top, well, potentially we've got 5 from S to M, 2 from M to N, and 2 from N to T. So we could send a flow of 2 from S to M to N to T. That means this would reduce now to 3, that would increase to 3, that would reduce to 0, that would increase to 3, that would reduce to 0, that would increase to 3. Along the bottom we've got 4, 4 and 2, so S, P, Q, T. We can send 2. That reduces to 0, that increases. That reduces to 2, that goes to 4. And that reduces to 2, and that goes to 2. So where else? We've got nothing now to send from S to P, but we do still have 3 here. So what can we do with that 3? Oh, we haven't filled this one in, have we? So let's do that now. So we've got an initial flow of 2 there. So 2, 3. So it could go up by 1. That's not actually any help though, is it really? So we can't get that 3 out because there's 0 capacity left here. There's 0 capacity to reduce along that way. So there's nowhere that the 3 can go. So that's all we can do. So that's us done with that part of the question. State the value of the maximum flow. So maximum flow equals, well, it was 10 to start with, we've added 4, so it's now 14, and it's litres per second. Always good practice to put the units in there. It then asks to indicate it on figure 5. So we've got a backflow here of 3 plus the minimum of 3. We add the backflows to the minimums, so we have 6 there. Here we have a backflow of 2 and a minimum of 6, so that gives us 8. So there's our 14. Here we have a minimum of 5 and a backflow of 3, so that's 8. Here, minimum of 1, backflow of 3, so that's 4. So from P to M, the backflow is 0, and the minimum is 2, so we have this flow of 2 here. From N to P, again backflow 0, so flow of 3 there. Here we've got N to Q, backflow of 1, minimum of 0. So you can see the completed values here. They should now all make sense. I'd check them just to make sure they do. 14 out of the source, what we expect, 14 into the sink. 8 going to M, 8 coming out. 8 and 3 going to P, 11, 2 and 9, 11 coming out. 8 going to N, 4, 1 and 3, 8 coming out. And 10 going to Q, 10 coming out. So job done. Final part of the question, find a cut with capacity equal to that of the maximum flow. So for the final bit we need to try and find a cut that goes through the network that separates source from sink that corresponds to the flow that we found of 14. So you're looking here for a cut of 14. Remember with cuts that you subtract the minimums when you have minimum capacities. So a little bit more difficult than normally where we don't have minimum capacities, where we only have to consider the maximums of the arcs going from the source to the sink through the cut. So looking now for where they're saturated going from source to sink, well, we can see that Mn is saturated, SP is saturated, NT is saturated. Well, we can't do anything from NT, so looking at these two, we can see that here, because there's 0 going directed that way, we could use that cut there. So that cut there goes like that. So Mn, the maximum is 8. PM is directed from sink to source, so it's minus PM, so that's plus 8, that's minus 2, and then SP is plus 8, so that gives us our 14. So there's the cut there, the cut goes through here. So find a cut. Well, that cut separates S and M from the rest of N, P, Q and T, and it goes through Mn, PM and SP. That's it.